well-defined included. It was a tornado cyclone that wasn't included at all, but had this bowl that's probably half-mile wide with suction boards like I've never seen before. It's like an octopus. And I think this is a unique storm because most of the time storms are translated, and they'll include and leave behind ropes, the rope tornado in the next one. So when they're moving slow, the inclusions don't get left behind. They get wrapped into the tornado vortex, and then that lower pressure, and then the overall mean lower pressure gets even stronger. Circulation-wise, you get a bigger pressure gradient, and it's kind of like jockling. Like we had a storm behind it too, and they kind of kicked the RFD around, and suddenly you had this massive circulation where the whole tornado vortex touches the ground. And a lot of people will say that you have a stick with a supercell, and you see a circulation, and then you see another one off the east, and like that's a new meso, but that's inaccurate. The whole meso is a much larger scale, and those are tornado cyclones that are forming. And this has been documented in Doppler radar too, and so it's fractal theory where everything has a similar structure all the way up at different scales. So like let's say you have a tornado that's shaped like this, and inside you have little miniature tornadoes that are spinning around called suction vortices that have similar structure as the main tornado, but different time and space scales. They last a lot shorter. And this tornado, there are 3 levels. There are these quarter-mile wide suction vortices rotating around like a merry-go-round, 3.6 mile wide circulation. And inside there are more suction vortices that are visible or not visible. And you could even see them on those close-range radar. You can see the quarter-mile wide circulation dripping around. May 9, 2003 was the tornado that developed in the eastern Texas Panhandle and didn't produce the tornado to Oklahoma City. They documented it with Doppler radar, and you can actually see the occlusions, or when the air goes through across isobaric flow, across isobaric, and you saw the occlusions in these tornado cyclones wrapping around like a merry-go-round and coming on the backside of the hood. It was a slow-moving storm, and this was one of those where it didn't leave any ropes behind in one tornado, and it was very unpredictable because it was just wrapping the whole occlusions into one massive occlusion. And you have so much stretching because instead of roping out and leaving it behind, it's not underneath the mesocycle, you don't have that stretching anymore. But when you keep pulling them into underneath the mesocycle, you still have those 100 meters per second updrafts that are stretching the vortices, increasing their intensity. And so that tornado, the quarter-mile wide one that was ripping around the south side, if you get like when a hurricane makes landfall, the right eyewall is most intense because you have to add the forward speed of the hurricane to it. So just like a tornado, imagine the F5 with a 300 mile per hour wind, and inside you have quarter-mile wide miniature tornadoes, each with probably 150 mile per hour wind. And inside there you have even smaller ones with who knows how much, 300 to 400, 2 to 4 times that of the parent vortex, but what is the parent vortex in that situation? And they're all translating at the speed of the circulation they're embedded in. So theoretically, and you should have wind speeds that approach the speed of sound on the east side of those miniature tornado vortices. They've never been measured in real life. They've been simulated by Dr. Fiedler at the University of Oklahoma. If you go home and do some research or Google Dr. Fiedler, F-I-E-D-L-E-R, suction vortices, you'll see a paper that simulates the tornadoes and shows the kinks in the suction vortices. If I have internet, I can show you a video of one we saw on May 17, 2013 in Young County, Texas, that you can see them so clearly. It's a rope, and it's helical, just like DNA strands. And they have a kink just above the ground. And it's counterintuitive because you think that friction would slow the wind speed down, but it's the opposite. Where the tornado interacts with friction, it causes vortex breakdown because it temporarily slows down the wind. And there's this thing called the Rossby radius of deformation. And so when you're below that spatial scale, the wind field adapts to the pressure field rather than vice versa. So you still have that low pressure, the wind is forced into the low pressure, and you still have stretching and it causes suction forces. And that happens on the tornado cyclone scale and the mesocyclone scale. So when you're out there storm chasing, you can see a clear slot punching in. That's punching across the ice because the low pressure intensifies so rapidly, and the wind field adapts to the height field or pressure field, where it's vice versa. So not the same. Does that make sense? I'm gonna ramble.